Get ready for an idea that is going to flip everything you think you know about something we do every single day. We're going to talk about the truly astonishing cost of a quantum glance.
Seriously, think about it for a second. What's the energy cost of reading a clock? It almost sounds like a trick question, right? I mean, you just look at your watch, you see the time. What could possibly be simpler? Well, as we're about to find out, when you shrink things down to the quantum level, the simplest actions have the most unbelievable consequences. So before we jump into the weirdness, let's just set the stage. Let's talk about the world we all know and experience every day. When it comes to keeping time, our world runs on a very simple, common-sense rule. In our normal, everyday lives, the rule is crystal clear. For any clock on your wall or on your wrist, the ticking, the actual mechanics of keeping time, that's what costs energy. That's what drains the battery. But glancing at it, just looking to get the information, that costs basically nothing. It's a freebie. And our intuition about this is built on centuries of these kinds of classical devices. A swinging pendulum, a vibrating quartz crystal. These are physical things happening, and they use up energy. In the process, they create what scientists call entropy, basically disorder, which is what gives time its forward direction. It's a one-way street. All right, but now we're leaving that familiar world behind. We are headed down the rabbit hole to a place where all those common sense rules about cost and observation get completely thrown out the window. Down here at this tiny scale, the rules of reality itself are just different. In this realm, the simple, seemingly free act of looking has a real, measurable cost. In fact, it can be the most costly action of all. Okay, so this is our clock. It's not gears and springs, it's a quantum dot, a tiny crystal made of just a few thousand atoms. Now, to wrap your head around just how small that is, imagine this. The size difference between this dot and a football is the same as the size difference between that football and the entire planet Earth. We are talking mind-bogglingly small. And here's the crazy part. To observe that impossibly tiny clock, scientists at Lancaster University needed all of this. A huge, complicated laboratory setup. The contrast between the thing being measured and the thing doing the measuring is just staggering. So, let's get right to the heart of it. What is the real price of just looking at something in the quantum world? What's the price of information itself? This really brings us to the central question, doesn't it? In this bizarre quantum setup, what's the main energy hog? Is it the energy it takes to run the clock? Or is it the energy it takes to just read it? And the answer is, well, it's not even close. It's absolutely astonishing. The energy it takes for this quantum clock to tick is tiny, almost nothing. But the cost to simply read it, to just pull out that piece of information, is orders of magnitude higher. It is a complete 180-degree reversal of everything we experience in our daily lives. And hey, this isn't just some wild theory. This is the direct finding from the researchers, published right there in Physical Review Letters. They found that the very act of measurement, that interaction between their big machine and that tiny dot, is the main source of energy cost and disorder. Glancing at this clock is actually the most disruptive thing you can possibly do to it. So you have to be wondering, how on earth did they actually measure this? Let's break down the incredibly clever experiment they designed that proved what seems totally impossible. First off, what does ticking even mean for a clock this small? There are no hands, no numbers. Instead, a tick is a single electron spontaneously and randomly jumping between two different energy states inside that quantum dot. Each jump is one tick of this little atomic stopwatch. So the process was basically this. First, they managed to isolate a single electron. Then they just let it do its thing, jumping back and forth, ticking away. Then, to read the time, they sent a tiny electrical current through a nearby detector to see which energy state the electron was in. And finally, and this is the most important part, they measured the tiny puff of heat that was generated by that act of reading. And this, right here, is the crucial insight. That tiny bit of heat wasn't just some side effect. It was the measurement. You see, heat is the most disordered form of energy, and in physics, that disorder is called entropy. So by measuring the heat produced, they were directly measuring the thermodynamic cost, the actual price in disorder, of pulling information out of that quantum system. Now, I know this might all seem very abstract and theoretical, but it has enormous real-world consequences, especially as we start designing our quantum future. So why does all this matter so much? Well, for starters, future quantum computers are going to be incredibly delicate. The heat generated just by measuring their states could be enough to mess them up and cause fatal errors. More broadly, it shows us that information isn't just an idea. It's a physical thing with a real measurable cost. And maybe most profoundly, it suggests that our arrow of time, that feeling we all have that time only moves forward, is deeply tied to the disorder created by the very act of us observing the universe.
Just to put a number on it, the cost of reading the system, of just getting that one little bit of information, can be more than 100 times higher than the cost of actually running the thing. That is a massive inefficiency that engineers are going to have to figure out for any future quantum technology. And that leaves us with one last, truly mind-bending thought. In the quantum world, it seems you can't just be a passive bystander. The act of looking isn't free. It costs energy, it creates disorder, and it fundamentally changes the very system you're looking at. So if a single glance can be that powerful, what does that say about the role that we, the observers, play in shaping the reality we're trying to measure? It really makes you think, doesn't it?